Okay, this is a video where I'm going to be covering periodic trends. So the periodic table, when you arrange it by increasing atomic number, we know we have periodic law. We get these repetitive things, so that elements end up in the same groups with similar properties. And I just wanted to talk about radius first. So radius is just the size of the atom. As you go down, you remember like n equals 1, 2. So you keep getting another energy level. So they're obviously going to get bigger going down a group. So the radius gets larger as you go down. And then when you go through a period, like let's say I pick this period, they're all going to have 3 energy levels, but they're getting smaller, which is kind of weird because they're getting bigger, in terms of their nucleus and their electron number, but they're getting more positive, so like phosphorus is going to be, let me grab my phosphorus would be plus 15, sulfur's plus 16, plus 17. So because they are not gaining energy levels, but they are getting a more positive nucleus, they're able to attract their electrons in more closely, which is why they become smaller. So the radius trend is that the atomic radius decreases as you go across, and atomic radius increases. And the reasoning is just like I said, and I'll say it again, going down the group, you're adding energy levels. So every level, and that's going to make them bigger. Going across, if you're within a period, you're not adding energy levels, but you are adding protons to the nucleus, which are more attractive to the electrons, which pulls them in more closely. And now, just looking at radius here, so we're going to compare carbon, fluorine, beryllium, and lithium. So the largest radius would be lithium. And then beryllium would be smaller because it has more protons to pull its electrons, then carbon, and then fluorine would be the smallest. So the largest is lithium. This is on your worksheet, and it is in the notes and in this video, but it's not in our textbook. So I would just make sure you grab this and fill it out, or you can put it in your notes and transfer it later. So we're talking about electron shielding and electron effective nuclear charge. Electron shielding is all of the inner core electrons kind of shield or get in the way. So all of these electrons for both of these are getting in the way of the outer electron. So if I look at just this one outer or just this one outer electron, they're both having electron shielding. There's these electrons getting in the way of the electron feeling that full positive force of the nucleus. But the shielding, in this case, the shielding is greater because let me think about this. There's the same number of energy levels, but the radius is larger. So this electron is further from the nucleus. So it's going to experience, even though it's just more shielding, even though there's less electrons, because it's so far away. So effective nuclear charge is, you can actually calculate this by looking at the charge of the nucleus and then kind of subtracting all of these shielding electrons. So then that's the charge that the electron actually feels. So we're not going to calculate it, but if that helps you to understand it, the formula is to take the atomic number minus all of the inner shielding electrons. But anyways, the effective nuclear charge is the actual net positive charge that the electron will experience. So essentially the inner electrons kind of cancel out the nucleus, so they don't feel the full positiveness of the nucleus. So this electron here versus this electron here, this electron's going to experience a higher effective nuclear charge because it's closer and it's got a more positive nucleus. This one over here is going to have a lower effective nuclear charge because it's further away, because the radius is bigger and the nucleus isn't as positive. So effective nuclear charge between silicone and chlorine will have a greater effective nuclear charge because it's got a smaller radius. It's got more protons. So the electron on the outside is going to experience more of that feel of that positive nucleus. Ionization energy is the energy needed to remove an electron. All electrons are attracted to the positive nucleus, so it takes some energy to remove them. We're only going to talk about first ionization energy, just pulling off that first electron. So here's where you can look at this example again. Is it going to take more or less energy to remove the electron from the rubidium, or more or less to remove the electron from the iodine? So the iodine is going to have a higher ionization energy and the rubidium will have a lower, which means it's easier to pull the electron off of the rubidium. It's harder to pull the electron off of the iodine. And that again is because this electron for the iodine it's experiencing a greater effective nuclear charge than this electron for the rubidium because it's closer to the nucleus and the nucleus is more positive. So the trend for ionization energy is that it's inversely related to the size. So it increases as you go across the period and it decreases as you go down a group. And my explanation, I kind of said it already, but just as you're going down the group, you're adding energy levels. So the electron is getting further from the nucleus, so it's experiencing a lower effective nuclear charge. There's more shielding electrons in the way, so it's easier to remove the electron, lower ionization. Across the period, you're not adding any energy levels. You're getting smaller because the nucleus is getting more positive and holding the electrons more tightly, so it takes more energy. The ionization energy increases because the electrons are being held more closely to their positive nucleus. So if I was going to have to pick between potassium and cesium, and is that it? So which one would have the higher ionization would be the potassium. Potassium has only N equals 4. It has 4 levels of electrons, whereas the cesium has N equals 6. So 2 more levels of electrons getting in the way. So the potassium is going to have a higher effective nuclear charge. The electron's going to experience that nucleus more positive than the electron in the cesium. And therefore, it will take more energy or higher ionization energy to remove the electron. The octet rule, why are we, sometimes they're pulling an electron off really easily and sometimes not. It has everything to do with the octet rule. So atoms will tend to try to get a full 8 valence electrons. So normally that ends with S2P6. So if the ionization energies of these noble gases, if I try to remove one, if you did the simulation, it was impossible because they're so stable. It takes too much energy to even record a value for the ionization energy. Electronegativity is got the same trend as ionization energy, but it has a different meaning. It's the electrons that are in a bond between 2 elements, and then what kind of ability do the elements have to attract the electrons. So on your periodic table, it's electronegativity is on the bottom right of every element. And it goes from 0 to 4.0, kind of like a GPA. So for example, fluorine, and I'm showing that with this blue, whatever person. with an electronegativity of 4.0 versus nitrogen has only an electronegativity of 3.0. So the electrons that are being shared in the bond are going to be attracted to the fluorine more. So if there's an electron between these two in a bond, who's going to attract those electrons more? It would be this element because it has a higher effective nuclear charge. And that's because it has a more positive nucleus, smaller radius. So similar to ionization energy, but you're not trying to remove the electron. You're just talking about the pull on the electrons that are being shared between them. So the trend is the same as ionization. It's going to increase as you go across the period, and it's going to decrease as you go down the group. So again, the reason it gets less as you go down the group is because you're adding energy levels. So the effective nuclear charge is decreasing. So the electrons are not feeling that positive nucleus as much. So the electron that's in the bond isn't going to feel it much either. As I go to the right, I'm not adding energy levels, but I'm getting a smaller, more positive nucleus of an atom. They're able to pull on their own electrons more so, and those bonded electrons being shared. So electronegativity, sulfur has a higher electronegativity than silicon. And that's because sulfur is plus, they're both going to have 3 energy levels, but sulfur is positive 16 for its nucleus, and silicon is positive 14. So if I were going to draw them just really quickly, the sulfur, is going to be smaller, and then the silicon is going to be bigger. So if I was an electron in between, I'm going to feel this nucleus pulling more. So that's why it has a higher electronegativity.